So today we're going to be discussing logs and their applications. That's like the general topic for the next few weeks. So the first thing we're going to do is introduce what is a log. So if we had 2 to the x power equals 3, the question is, what is x? So 2 to what power is 3? And I think we could reason through it that 2 to the first is 2, so it's not 1. 2 to the second is 4, so it's not 2. So because doing 2 to the first yields 2, doing 2 squared yields 4, 3 is somewhere in between there. We're going to know x is somewhere in between these two numbers because 3 is in between 2 and 4. And unfortunately, it's not as easy as saying, oh, it's halfway in between, because 3 is halfway in between 2 and 4. It's not going to be a direct correlation, but we do know it's somewhere in between the 1 and the 2. So the question is then, how do we solve for x? The problem with doing traditional solving is if I have 2x equals 3, I could say, oh, well, you could divide both sides by 2. But the thing is, 2 to the x divided by 2 is not x. So you kind of get stuck because 2 to the x divided by 2 to the 1 is just 2 to the x minus 1 because you'd subtract those exponents. It doesn't behave the same way as if it was 2x. So logs help us answer the question, how do we solve for x? So logs help us to solve exponential equations because logs are the inverses of exponential equations. I'm going to say this a lot this chapter because logs are inverses of exponential functions, we use logs to solve exponential equations. So for example, we can take 2 to the x power equals 3, and we can rewrite that as a log equation. And that is a log equation is log base 2 of 3 equals x. So these two equations actually are the same equation, algebraically speaking, but they are different forms. So that is the conversion between an exponential equation and a log equation. And the reason why we do that is because x is now solved for. I now have x by itself. So I'm able to then calculate log base 2 of 3, and I have my answer. And so this is the generalized relationship. If I have b to the y equals x, then y equals log base b of x. And so I have to, what I call, jog around all of these different parts. I have to move the b, move the y, move the x to get it from exponential form to log form. And notice the base stays the base. So the base of the exponential here is the base of the log. So that keeps its essence there. Base is still the base. What is on the right side of the equation, the x ends up being on the inside of the log. And then the exponent is what that log equation equals. So that is the conversion between exponential form to log form, and that allows us to solve log equations. So the first thing we're going to do is get some practice with writing things in one form and moving them to another form. So we have log base 3 of 9 equals 3. An exponential, it's the base, which is 3, to the exponent, which is 2, equals 9. So one is exponential form, one is log form, but again, they mean the same thing. They are algebraically equivalent. So notice where the 3 goes, where the 9 goes, and where the 2 goes when you go from log form to exponential form. In part B, you start with log base 2. And that 2 you write small, it's like a subscript, like in chemistry, like H2O, the 2 goes in that same spot. Log base 2 of 32 equals the exponent, which is 5. So log base 2 of 32 is 5. And so that basically says 2 to what power is 32, and it's 2 to the 5th. Next, we have log base 5, because the base is the base, of 9 equals the exponent x. So that's going from exponential to log form. And then lastly, we can go again from exponential form to log form. So I'd say log, and then the base is 1/4 of 16. So of that 16 goes inside of the log, and that equals 3x. And so this gives us a lot of flexibility with solving. Notice in part C, right there, I have 5 trapped as an exponent, but when I go to log form, it's no longer an exponent. It's already solved for. Notice in D, I now can solve for x, because I could just divide both sides by 3. So what going to log form is it frees numbers from exponents. So logs and exponents are inverses of one another. So for example, if I plug in 4, the function is 2 to the x power, 2 to the 4th is 16. So going from one function to another, log base 2 of 8 is 3. So I can take powers of 2, 2 to the 4th is 16, that's why I put the 4 here and the 16 here. 2 to the 3rd is 8. But what this means is log base 2 of 16 is 4, log base 2 of 8 is 3. One maps to the other maps to one. There's only one answer for each, and they map back and forth to one another. Unlike quadratics, where if you square something, if you square 5, it could be 25. If you square -5, it could be 25. So there's multiple answers, multiple ways to get x squared equals 25. Here, there's only one way to get each of them. 2 to the 4th is only one answer. Log base 2 of 16 is only one answer. And those two connect. They're inverses of one another. And we're going to continue to explore this, but for now, I'm just kind of giving you that information. So now we're going to learn to evaluate logs considering the exponential form. So what you ask yourself when you see something like log base 4 of 16, what you're asking yourself is 4 to what power is 16? So log base 4 of 16 is asking the question, and again, we're looking at exponential form, 4 to what power is 16? So, yep, we would get 2. So a lot of logs, especially if they're set up in a certain way, you can just do in your head. If you know the answer to the log is an exponent, then you can get there. So for B, it's 10 to what power is 0.001. That is 1/1000th. If you want to write it as a fraction, you could have kept it as a decimal. So 10 to what power is 1/1000th? So we're going to have to consider going to negative exponents, because negative exponents are what put that, that 1000 in the denominator instead of the numerator. And so if we consider like 10 to the -1 is 1/10, 10 to the -2 is 1/100th. Yeah, so that one's going to be -3. Okay. Next we have 1/2 to what power equals 8. This one as well, we're going to need a negative power, because if we just take it to positive powers, it's still going to be 1 over some power of 2. So what do we think? 1/2 to what power would be 8? Yeah, it's going to be the negative third power, because 1/2 to the third power is 1/8. 1/2 to the negative third power, we flip it over, and that's 8. Next, we're going 16 to what power is 4? So something we have to remind ourselves of is that the square root of 16 is 4. So that's actually going to help us. The square root of 16 is 4. So the square root of 16 is the same as 16 to the 1/2 power. So taking a square root is the same as taking something to the 1/2 power. Okay, so that's going to be 16, or I'm sorry, 1/2. Because 16 to the 1/2 power is the same as the square root of 16, which is 4. Now this next one looks a little weird. It's log base e. Log base e would say, and e is that special number, it's like 2.7. So we'd say e to what power is e to the 4th? Yeah, it's just 4. It's almost so easy, it looks like a trick. So again, e to what power is e to the 4th? That's just going to be 4. And then lastly, we're looking at 3 to what power is 1/27th? So we're going to need a negative power that will make 3 1 over. So 3 to the negative 1 is 1/3. 3 to the negative 2 is 1/9. Yeah, so it's going to be -3. So when you see those fractions, you're going to have to remind yourself that that's going to require a negative power. So there are 2 logs that come up all the time. One is log base 10. Log base 10 comes up. It's actually how we deal with our number system here. When we think of tens, hundreds, thousands, millions, we use those particular ways to characterize numbers. And those are all powers of 10. 10 is 10 to the 1, 100 is 10 squared, 1,000 is 10 cubed, etc. So 10 is used so much in our counting system. If you do log base 10, that's called the common log. And actually, they allow you to write it as just log of x. So if you see a log without a base, that means it's base 10. And it's called the common log. The natural log is used to qualify and to describe all sorts of natural phenomenon. So a lot of things in nature, things that are continuously changing, evolving, reproducing, those require a natural log. So natural log is log base e, so it's written as log base e, but because it's used so often, it gets a special name for a log, which is ln. So that is an L, not an I. I often use like the curly L to denote natural log. I think it's French, like log de naturel, and that is, excuse the French there, it's probably terrible. But it's just given because it's a naturally occurring number. So log de naturel means log base e, and e is about 2.717. That's a rounded number, just like we have to round pi. And again, it occurs in all sorts of natural phenomena used in bio and chem a lot. Okay, so with that, we have the inverse property of logs, and this is for logs of any base. But if you take the log base a of a, the log and the exponential actually cancel each other out. So log base a of a to the x is just x. So because logs and exponentials are inverses of one another, I think of the log and the exponential kind of absorbing each other or canceling each other out, and out pops that x. So notice if the base of the log and the base of the exponential are the same, they're going to cancel out. Likewise, we have a to the log base a of x. Notice these have the same base. They're both base a. So we have the base a here of the exponential and the base a of the log. And if those agree, those are going to cancel out and you're just left with that x. You're left with the thing that's not the a. You're left with the input of the log. So again, if you have a base and an exponential that's equal, the answer is just going to be either the exponent or the log input, basically the non-a value. So take a look at example A. We have natural log, or ln, of e to the fifth. That's the same as log base e, because we know natural log is log base e of e to the fifth. So since the log base and the base of the exponential are the same, right there, they're both base e, the answer is just 5. How about B? Yeah. So for B, you'll note that the base of the exponential and the base of the log are equal. So the bases, basically the exponential and the log, cancel each other out and just out pops that 5. Okay. So now we're going to do some log evaluations of the common log and the natural log. So I want you to remember that if you just see log, that means log base 10. Log base 10 of 100 means 10 to what power is 100? Yep, it's a 2. 10 squared is 100, so log of 100 is 2 because 10 squared is 100. Now, ln of e is the same as log base e of e. So log base e of e means e to what power is e? Yeah. So back in when I was in high school, I just had to memorize ln of e was 1 because I didn't really understand it. But if you understand what natural log is and what a logarithm is asking, you can see that it's 1. You don't have to memorize it. So that was great. Next, for C, we have log of 1/1000th. So the base is assumed to be 10. You can even write it in there as 10 to just remind yourself. So again, you're asking 10 to what power is 1/1000th? -3, because 10 cubed is 1,000, so we have 1/1000. Right. Yep, you're just counting the zeros. I learned that trick really late in life. Okay, so for D, it's 10 to what power is 45? Now we know if we're thinking about this, 10 to the first is 10, and 10 to the second is 100. 45 is somewhere in between there, between 10 and 100. So that means this log is going to be somewhere in between 1 and 2. Because 10 to the 1 is 10 and 10 squared is 100. So since we don't know exactly what it be, we're going to use our calculator. So I'm going to bring up the calculator now. And you'll notice on your graphing or your scientific calculator, it has a log button. So I'm just going to show you where that is. And we're expecting a value between 1 and 2. So I'm going to go to my quit screen, which is second mode, clear this out, and I'm going to type in log. Log is to the left of the 7 of 45. And then I get 1.65. You could round to like the nearest hundredth or thousandth. But the only way to do that exactly without something really arcane called a log table is to use your calculator. So that's where it comes in real handy. So it's going to be 1.65 for that one. And then ln of 16, that would be asking yourself e to what power is 16? And e is a really strange number. It's like 2.727, and it just keeps going. So it's not an easy way to calculate this in your head. So I'm just going to go ahead and bring up my calculator and type in ln of 16. ln is to the left of the 4. And then I get 2.77. And so you'll notice most of these I could do in my head, but not all of them. So if you're doing a log of base E or base 10, you have your calculator to use for that. All right, so this is the assignment. That is all.